to go ahead and record because there's so much to get through today. I want to be able to post this later in an announcement so that you can go back and catch anything you might have missed. All right. So our objective for today, we are going to talk about grades. We're going to talk about all kinds of parts for waves. We're going to basically come up with a set of rules for identifying the parts of a wave. Many of you should have seen waves before. Usually you see waves in elementary school, about 5th grade or so, and then you see it again in 7th or 8th grade, and now you're seeing it again. So, but usually when you see it, you only see transverse waves. You only see the normal like ocean wave kind of a thing, and a lot of the stuff you learn is very basic. And so now we're going to get into all the different types of waves you can see. So we're going to talk about what are the tests for things that work for every wave. Then I'm going to give you feedback on your claims, because most of you are writing the wrong thing for your claim. And then if you write the wrong claim, then none of your other stuff is probably very valid or very good. So we probably won't have work time based on what happened last block, but we'll see. Okay, so grades. Keep working to get things turned in. You got until tomorrow at 8 p.m. if you want it to go on your report card. However, if you don't make it in time, don't stress about it. Just get it done as soon as you can, because I will still take it after tomorrow. All right, if you do have a specific question, you can chat it to me with a private message. Otherwise, let's talk about waves. So I'm not going to go into great detail on this because it's in your video notes. It's also in one of the, it's in the weekly overview video that I talk about some of this stuff. So if you have not watched that, well then you missed out. But here are our quantities in units. So we're going to talk specifically about what these, how we actually figure these things out. But there's amplitude, wavelength. This is the Greek letter lambda, which I explain how to write it in my other video, but it's like a little squiggly line with a little kickstand, okay, lambda. Frequency, we use the letter F in physics. In chemistry, I usually use a different Greek letter called the nu, which is that, but we won't use that in this class. But you might see it when you talk about waves in chemistry. Period is capital T, not lowercase, capital T, and speed, and it's the speed of a wave. Here are the 4 equations. They are on your equation sheet. So if you don't have these down, you might want to write these down right now. They are on your equation sheet, but sometimes it's nice to have them in your notes. Okay. Frequency equals 1 divided by the period. Period equals 1 divided by the frequency. The speed of a wave equals frequency times wavelength, or wavelength times frequency. And the speed of a wave also equals frequency divided by the period. This is the one we're going to use the most, okay? In chemistry, you actually use the speed of light equals wavelength times frequency. But it's the same equation. It's just the speed of light is a constant. It's a set number, never changes. And then we use wavelength and frequency, and we could figure out things about it from there. Okay, so if you've got these 4 equations down and you're ready to move on, give me a green check. Since we haven't done that in a while, make sure it's down in the bottom of your Zoom window, and you can click on the, go to participants and click the green check. Okay, this is an equation we will not use, but energy of a wave is h times the frequency. And h is also a constant. So let's try this one. This is one that you should actually know. You should have known before coming to this class because of previous science classes, but it's okay if you didn't. But I want you to tell me, how do I find the wavelength of a wave? So we're going to actually come up with the rule we can use for any wave, but I want to see what you think right now. What do you think right now? How do I find the wavelength? You can even use this drawing down here to help you explain it. So we've got this wave here, down here. So not the mathematical definition. How do we actually, looking at that picture, how do I know what the wavelength is just by looking at that picture? What would I look at? Most of us got something. So let's take a look at what a couple of you have said, and then we'll come back and talk about it. So I'm gonna pause you for a second if you are typing. So this is the top, both of these are what you should have learned back in elementary school even. The distance between the two crests or two troughs. More easily said, probably measure from crest to crest or trough to trough. Which means we got to know what a crest and a trough is, which I don't know if it actually talks about those in the video. I forget. But the crest is the top of the wave. So from crest to crest, if we measure that distance, we would have the wavelength. Or we could go from trough to trough. We could measure that distance and we would have the wavelength. As long as this is a standard wave, this wavelength up here should be exactly equal to this wavelength right here, okay? It actually doesn't matter where you do it as long as it's crest to crest. Okay, now that works for very basic waves. So when we start talking about longitudinal waves, it can get a lot harder to figure out what's going on. And if you ever have done any sound recording and you look at a sound wave, you actually get this weird squiggle. You get a complex wave, and now where is the wavelength? Well, it's actually changing as the sound goes, okay? And so you have to there's multiple wavelengths and different, so it can get very complicated very quickly. So what is the actual rule that we're going to use? Well, before we can find that, we need to figure out where is one wave. So in the chat, where would one wave start? So just tell me which one of these shows one wave. So does A, from here all the way up to here, is that one wave? Or is this one wave? Or is the orange all the way down here one wave? So A is correct, but there's another one that's correct. So is it B or C? Which one is the other wave? Okay, and the answer is going to be C. So let's talk about the difference, what's going on here, okay? So letter B was actually one pulse, okay? One pulse. You have one hump or one oscillation, or it's actually not even a full oscillation, it's a half an oscillation, but one hump of a wave, because that's how you think of it when you look at it, is one pulse, but that's only half the wave, okay? By definition, a wave is when the motion repeats itself. Where does the motion start to repeat? So if I start here and I trace the wave, where does it start over? Where does it start doing the same thing again? Nope, I'm going downward. It's doing something different, doing something different. Oh, now I'm going to start over and I'm going to go back up again. So from here to here is actually one wave. Well, guess what? That distance is also known as a wavelength. Okay, so the wavelength is the length of one wave. So we say crest to crest when you're in elementary or middle school because it's easy to remember and it works 99% of the time. So let's take a look at it. If we start here, where does it start to repeat? At the next crest. At the next crest, the motion starts to go down, down again. So it's repeating. So this is one wave, okay? If I start at the trough, down here and I go up, where does the motion start over? Down here at the next trough. So trough to trough, crest to crest. Those are the easy ways to remember it, but in more advanced applications, you may only be given this part of the wave. The rest of it might be not even there, like it's all marked out. So pretend that that's not there, pretend that that's not there. Well, how much of a wave do you have here? You only have half of it. Because when it comes down here, it's going to keep going down and then come over here and then repeat. Okay? So how do I find the wavelength? It's the length of one wave, and it's where does the motion repeat itself? So the test is, where does the motion repeat itself? So I could actually start here and go, well, where is one wave if I start there? Well, you go until, where does it repeat? Right there. Now it starts over. That's the wavelength. The distance between those 2 points in a straight line there is the wavelength, which is equal to this wavelength, which is equal to this wavelength. It's one of the beauties of waves is that once we know the wavelength, we know the wavelength for the entire wave. For each section of the wave, we know the length of it. Okay? And a wave, a longitudinal wave, is made of 2 pulses. Okay? So we got the one pulse going up, but then we got the reflective pulse going down. Okay? So the one wave is really basically 2 pulses. Okay. So now let's go to the challenging question. That should have been kind of a review and a clarification, but now let's take a look. We've got a longitudinal wave and a transverse wave. Okay, so first let's make sure we're clear on what a longitudinal wave, and then I'm going to ask this question. Okay, so don't answer it yet, but in a second we'll answer this. What's the wavelength for a longitudinal wave? But first we got to know what is that. This wave down here is what you usually see when you talk about waves. So this one up here is a lot harder to understand. But if you think of it like a slinky, okay, you will get it. But what you need to understand for both of these is the energy is going from one end to the next. So it's going down the rope. So I hope we've all gotten a chance to do that. And if you don't, you need to do this for yourself. But get like a jump rope and then make some waves with the jump rope. Well, what do? When you strike the jump rope, the little hump travels down the length of the rope, right? And if you strike it a bunch of times, you get a bunch of, you make it like a snake, okay? You make a bunch of humps traveling down the rope. But that wave goes in that direction. So if you're looking at the video camera in your Zoom, the wave travels in that direction. That's the travel of the energy. Okay, the energy of you, the work you're doing by striking the rope sends an energy pulse down the rope. Okay, so it's traveling that way. But which way does the rope actually oscillate or move? It moves up and down like this. So the energy is going this way, but the rope is going up and down like this as it goes down. Okay, so if you do this with your hands and then turn, guess what? You make the letter V, almost like you're a cheerleader, okay? You got the letter V. So transverse is actually a perpendicular wave. So the energy is going this way and the oscillation is going up and down, okay? And so you turn and now you got your V. Another way to think of it is energy is going this way and it's perpendicular, the oscillation, the up and down. And if I turn my little perpendicular sign to the side, I've got the letter V for transverse. It's a little funny way to remember it. It's an important way to remember it. Okay, so now longitudinal is different. The pulse is still going to go that way. The energy is still going to go this way. Okay, but the oscillation, the movement of the particles is going to be in the same direction. So the energy goes that way. The object is going to oscillate like this. Okay. So it's along the energy transfer. It's along the energy transfer, longitudinal, okay? Another way to think of it is if you write it lowercase, longitudinal, if you print it and you take out that L and you write them next to each other, you've got the sign for parallel from your math class. So longitudinal, it is parallel. So it goes in the same direction. Energy transfer, oscillation, it's along, it's longitudinal, okay? All right. That still can be confusing as we go forward because we've got to understand this, that in a longitudinal wave, we've got a bunch of particles sitting here. And let's say I clap my hands really loud. I hope that didn't hurt anybody's ears, but clap my hands. Well, when I do that, I basically created a sound pulse. And this air particle strikes that particle and causes this particle to move. And it causes all the particles to move that way. But the particle doesn't move and then stay there. It moves back. It comes back to its starting point. Okay? So these particles are doing this. Compress, compress, but then it moves back. So it compresses and stretches. So if you ever take a slinky and stretch it out, and you're not shaking it back and forth like a snake, you're actually pushing it, and you'll see the slinky compress like this. And hopefully I'll find a video of that to show you and make sure we are very clear on that. Okay. So I just wanted to lay that groundwork. Now, what's the wavelength? How do I find one wave on a longitudinal wave? What's the wavelength, or how do I find one wave? Now type that in the Pear Deck if you have not. Ah, excellent. You said it like a question, but that's exactly correct. Okay. You guys are thinking, I like it. I'm gonna go ahead and pause you if you're typing, and let's take a look at what some of you said. Wavelength goes from one compressed area to another, where a pattern repeats itself. That's the technical way to think about it. So pick a spot on the wave, and where does the pattern repeat? Okay. It does happen along the energy transfer. Measured from where the object squeezes together to when the object squeezes together again. That's a great way to say it. From the point with most compression to the next point with the most compression. I like how you're being specific in most of those answers. So really well said. But I do think the best way to think about it is, where does it repeat? So I can pick any spot along this wave. So I could pick, let's see, let's just pick this line right here. Well, where does that line, basically that kind of compression, happen again? And it may be hard to find because we would have to count lines and all that stuff, but just approximating, that's where it repeats. Now, someone said most compression. So we look to the middle of the compression and then go to the next middle of the next compression. Wavelength. One wave. Wavelength. One wave. But I could do the maximum uncompression, where it's maximum stretch, and go to the point of maximum stretch. Okay? And got wavelength. But it's where the motion repeats. Okay? So we got compressing, stretching, compressing, stretching. Okay? Wherever that repeats is where we look. So I could look at the front of the compression. So when we think of sound waves, we think of compression waves. Okay? So we could go from the front of the wave to the next front of the wave. Or we could go from the middle to the next middle. All right, let's take a look at the next part of a wave though, and see if I can confuse you. I mean, not confuse you. Amplitude. What is amplitude? So let's start with the transverse wave, because those are usually easier to find. What is amplitude? We can go from here to here. Which one is the amplitude of this wave? A, B, or C? Hey, it's all good. I'm being tricky on purpose. A is the correct answer. But Brianna brought up an important word that we have to know to really honestly figure this out. And it's basically, what is this line called? And in your notes, we call it equilibrium. Equilibrium. But there's actually another word for it that we could use. Okay? That's actually, I think, a better word for understanding. Equilibrium is more correct, more exact. But there's a word that I think will help us understand it better. And it's called the rest point. So if, using the jump rope analogy, if I have a jump rope, before I send the pulse or start shaking it and make the snake, okay, and make the humps go down the rope, the equilibrium point, it would be the resting point of the wave. So where is it at rest? Well, the resting point is in the middle, okay? And so the amplitude is how high, what's the displacement from rest? So it's from the middle to the maximum displacement from the resting point. Okay, so that's amplitude. Someone asked this question earlier about amplitude. Amplitude for sound determines how loud it is. So I know I use my teacher voice even though I've got a microphone, and so it can be pretty loud, which means lots of energy, which means large amplitude, which means loud. For light, large amplitude means brightness. Okay, so the brighter a light is, the more energy is being put into that wave of light, and it appears brighter. Okay, amplitude, distance from the resting point. All right, now let's look at the longitudinal wave. What's the amplitude on the longitudinal wave? Okay, so let's just keep it that what would be the resting point? So we have to really see this, and that's the problem with this drawing, is where is the rest point? So for example, this particle right here that's compressed, well, at one point it was not compressed, okay? So in theory, this particle is actually gonna move and then move back. Okay, so where is its resting point? Okay, now, honestly, with the way I drew this, its resting point is probably here in the middle somewhere. Okay, so a piece of energy, like I clap my hands really hard. When I clap my hands, something comes and causes this particle to move, and then it moves back past the center point, and then it moves back to the center point. Eventually, it will stop and come back to the resting point. So the amplitude is how far from rest is it? Okay, so the definition of how far from rest still works. It's just really difficult to find on a longitudinal wave unless you know what the resting point is. Like on this wave, it's really easy. Well, there's the resting point, there's the amplitude. On here, how do you find it? That can be challenging, okay? But it's still the same idea, okay? All right, we're gonna keep moving. Okay, frequency. So I'm just gonna tell you the test for frequency because of time. So the frequency is, I get this backwards sometimes, okay? How many waves in 1 second? So I've got my wave here. And now I'm gonna look for, okay, we started here, and then here is 1 second. 1 second. It's like we're sitting there with the jump rope and I watch you make the wave and I time it. At 1 second, this is how much of a wave I have. Well, I have one wave in 1 second, and that's literally the definition of a hertz. So that's 1 hertz. I hope your brain doesn't hurt too much. Pun intended, okay? 1 hertz, 1 wave in 1 second. Okay, so let's kind of reset this a little bit. If I have, actually, let's reset the whole thing here. If I actually start here and I go all the way to here, how many waves do I have in 1 second? So this is 1 second. How many waves do I have? I have 1 wave. I have 2 waves. So this one would be 2 hertz. Because in 1 second, I have more waves. So frequency is waves in 1 second. All right, so quick question for the chat. What's your favorite radio station if you have one, or if you don't get to pick the radio station in the car, what do you wind up listening to because your parents are listening to it? 93.3. Looks like quite a few of you put that one. 93.3, whatever the station number is, that's actually the frequency of the station, and it's in kilohertz. So way back in the very first unit, we learned that kilo means 1,000. So that means 93,300 hertz. But what does that mean? That means in 1 second, there are 93,300 waves that make up that radio frequency. So radio is nothing but light. It's a wave of light that's has this many waves in 1 second, 93,300. So 103.7 FM would have 103,700 waves in 1 second. By changing how many waves are in 1 second, we can send discrete, separate channels of radio, and we can send those out, and now you can pick what station you want to listen to, okay? Your internet at home works on a similar thing, but we're talking gigahertz. So if you read the gigahertz, that's telling you what the frequency of light is that it's putting out. So all cellular signals, all Wi-Fi is basically different kinds of light that work at very, very high frequencies compared to radio. And it's all light that we cannot see with the human eye. Okay, so let's talk about the period of a wave. So the period of a wave, time of one wave. There we go. I knew I was getting it backwards. This is why we talk about it. Time of one wave. So frequency is how many waves in 1 second. So frequency is waves per second. And period is seconds per wave. So this is period, and this is frequency. So it's period is the time of one wave. So you have to find one wave and then find out how much time there is. So if I start here and I find my one wave, but I look at it and it says that is 0.25 seconds, then my period is 2.25 seconds. So it's what's the time of one wave, okay? So in this one, we're famous for giving this kind of a question on the test where we only give you this much of the wave and ask, what's the period? And you're like, wait a second, that's not one wave. Okay, so now I gotta, so if this time is 1 second, well, what's the period? Well, that's a quarter of a wave. There's half the wave, 3/4. There's the full wave. So how many sections of that is there? There's 1, there's 2, there's 3, there's 4. So 4 times 1 second, so the period would be 4 seconds because we are looking for the period of the wave. What would the frequency be? The frequency would be 0.25 hertz because we have a quarter of a wave in 1 second, okay? So we can actually use our equation. T equals 1 divided by 0.25, which equals 4 seconds. And we can use F equals 1 divided by 4, 1 divided by T, and we get 0.25. Hertz. So if you know the frequency or the period, you can find the other one by using your equations. But I like to be able to look at it and think through what it looks like, okay? So period is the time of one wave. Frequency is how many waves per second. Honestly, because of chemistry and the work that I've done with teaching chemistry, I prefer to look for frequency first because it's easier to think about for me. And then I plug it into the equation period equals 1 divided by F, and then I find what it is. That's just easier for me because this is easy to think about. How many waves are in 1 second? So I find where's 1 second? Okay, how many waves is it? Okay, that's the frequency. Okay, and then I do the math to find period. But you can do it the other way too. Let's see. All right, so here are the 4 tests that we just talked about. So if you need to write those down, now would be a great time to write those down. I'll give you about 1.5 minutes, 2 minutes to get those written down if you don't have it. But I would add that to my notes somewhere. All right, looks like I got enough green checks. So I'm gonna go ahead and press on. I am making a video, so if you don't quite get all of this written down, you can come back to that shortly after class is over. Also, when I turn the Pear Deck to student pace, you can go back to that slide. It's amazing how it all works and how it all stays separate and gets to the right place. Bluetooth, radio, wireless internet, all those things are happening at the same time, and for the most part, they make it where they're trying to go. Okay, so let me highlight these questions, and then I'll make sure I answer them. All right, I'm gonna share these, and so I'm gonna pause you if you are typing, and so we can focus on these questions. What is a medium? Okay, so a medium is the material a sound, or not a sound, a wave passes through. Okay, so sound waves, for example, must have a medium. They must travel something. So if you're in outer space where there are very small numbers of particles, there's basically nothing to carry sound. So when you watch like Star Wars and you hear all the explosions in space, there's no sound in space because there's no medium, there's no particles, okay, to transmit the energy. If you're inside the spaceship, you got air, you got stuff like that. So yeah, there is air, there's a medium for it to pass through. If you've ever watched an old Western and you'll see the guy put his ear to the ground and he's listening for hoof beats on the ground. He's listening for horses or animals on the ground. You can actually do that, and you can actually hear sound better through the ground. So same principle of putting your ear up against the door and listening through the door. Sound travels through a physical object, through a material, because the particles, the atoms in the material, are given an input of energy, and the energy travels through the substance and it gets to the other side. Now, there's things like friction and stuff where the sound doesn't travel forever. Okay, eventually it dies out, okay, because of friction. But a medium is what it passes through. Light also is affected by a medium, but light does not require a medium. That's how we get light from the sun. The light from the sun is passing through empty space. It's not quite empty, but for the most part it is. Okay, it doesn't require a medium and it still gets to us. However, you put the pencil in the glass jar and you see that it looks like it's in a different place. Well, that's because light is traveling through water and not air. And so it has a different effect on the wave of light. Okay, electromagnetic waves, continuous waves. So how is a pulse created? A pulse is actually, and I'm getting this because it actually answers the continuous wave. A pulse is created when there's basically any input of energy, okay? So it can be very complicated and quite a different range. The most simple one that we look at is like the slinky or the jump rope example, where you put an impulse, you put in some work, which creates kinetic energy, and the energy travels down the length of the rope, and sometimes it comes back, but it travels in a pulse, okay? And 2 pulses make up a wave. So a continuous wave is something like light, where once you turn on a light bulb, the wave is continuous from the source all the way to the receiver of the pulse. Even a sound wave. The sound coming from me to the microphone, that wave is a continuous wave. Now, if I just clap my hands, and this is where it gets complicated. If I clap my hands, there's only one pulse because there's only one input into the wave. but it actually will cause a complete oscillation in the air. So if I were to draw it out, it would look like you could actually mark out the full wave. So, and I don't want to confuse you by that, but there's actually only one pulse in that situation. But I can actually map out the whole wave because all I need is the information from the one pulse to draw out the rest of the wave. So a continuous wave is one that in our class, we're going to pretend like goes to infinity and beyond. It never stops. Okay, that's a continuous wave. Electromagnetic waves are waves that are, it's actually a dual wave where you have an electric wave that's going one direction, and then you have a magnetic wave and they are perpendicular to each other. Okay, so I can't draw in 2D because it's actually a 3D wave, but you have one wave going like this, up and down, and then you have one wave coming out of the screen towards your face and then away from you, and then towards you, and then away from you, and it's in 3D. And it's at right angles. So this is 90 degrees in 3 dimensions. That's actually not a bad 3D representation. Okay, that's an electrical magnetic wave. What's the easy way to say it? Electromagnetic wave is light. It's just there's some types of light that we can't see. Okay, so electromagnetic waves are all types of light. So Roy G. Biv, red, orange, yellow, green, blue, indigo, violet, the colors of the rainbow, those are all electromagnetic waves. All right, we are almost out of time. Okay, Bluetooth. I'm not going to explain it, how it fully works, but basically the digital signal is turned into a set of a wave, and it emits that from your phone, and that wave goes to the Bluetooth device, say your headphones. Your headphones convert that wave. It actually, we'll talk about this next unit too, but it causes a magnet in your earbuds to vibrate with the same types of frequency as the actual music that you're listening to, and it recreates the sound. But Bluetooth operates on a set frequency that's different from your cellular signal, and it has a different amount of energy, which means it has a different amount of range and those kinds of things. But it's basically a wave of light. Okay. Which means it doesn't matter what the medium is, it can travel through it for the most part. Okay. Light does have sometimes a hard time though going through some solid objects. Anyway, all right. We need to get on to the next thing. We can come back to that. We're going to come back to that question next unit as well. All right, claim. The number one problem with the claim is a lot of people are just writing the question or the title of the TED Talk again, and that's not the claim for most of you. Some of you it is, but many of you it's not. The claim is not the question, it is the answer to the question, or it's the main idea, okay? So, and then we're gonna look at words that are really important to the claim for our definition. So I'm gonna share with you a great example from a student who did a pretty good job, and I want to show you what they put, okay? So this one, what if everyone jumped at once? That's the question, but here's the claim. Almost nothing happens when everybody jumps at once. That's the answer to the question. And then when they did their definitions, we're talking about jumping. Well, what does it mean to jump? He brings up time because we're talking about jumping at the same time or at once, okay? And we are talking about the earth and not some other type of system, because that could make a difference. And that's kind of part of the question, but that's really important to the claim. Okay, so let's take a look at the next one that he wrote. Because there's a part, this one's not completely correct, but it's pretty good. What is the coldest thing in the world? The coldest thing in the world is, so this is where it is, but it's not what the object is. So now I don't know if they actually use this word in the video because it's been a while since I've watched it. but it is the Bose-Einstein condensate. But I know they do talk about something specific. Einstein condensate, the fifth state of matter. Okay, that word may not be used in the video, but they will certainly talk about a coldest object. They talk about what's the coldest object. So it's not laser beams. Laser beams cause the thing to cool down, okay? So you need to watch carefully for the main idea. What is actually the answer to the question for this one, okay? So some of it you may actually have to watch the video all the way through before they actually answer the question. So that's what makes this a little challenging. That's where most of you need to go back and take a look at, okay? And because it was such a major issue or error, I did not mark this in your homework yet. So I'm telling you now, so if you need to change it, go change it, especially for your final draft. I mean, you can change it in your homework and that's great too, but especially in your final draft, you need to fix that, okay? So here's one that's another great example, and then we're done with class, but the dark history of bananas. The actual claim is this: bananas carried a disease making them dangerous. That would actually be a claim. This is just like a hook or an attention getter to make you kind of go, well, what is that about? Okay? All right. We are out of time. So what I want you to do, there will be a quiz tomorrow, and it will be all vocab and stuff we talked about today. But in the Pear Deck, what's your main takeaway from today? Tell me how things are going for you. And I'm going to turn this to student paced. You can stick around for any more questions. But that's all I've got for today. And I will see you next week that I just chatted to you. Now, so all it means is that all the particles stop moving. So normally when something gets cold, the electrons are still orbiting the atom, still orbiting the nucleus of the atom. But in a Bose-Einstein condensate, it gets so cold the electrons actually stop moving too. And when they stop moving, the atom collapses and you get this blob of matter.
Oh.
Only way to make it that cold is to use lasers to cause it to cool down, which is not what you think of when you think of lasers. Anyway.